We will start here after ring and field. ring. When we are entering ring and field, so group theory, we saw more number of groups under different operation, addition, multiplication. Or another operation also. But when we are entering ring, just you think from group theory, only we are choosing groups under addition who is abelian groups. That groups and all we are choosing and we are entering ring. Otherwise, other non-abelian group, first no need for ring and field, non-abelian group. Abelian group also, every abelian group we no need for ring and field. Which abelian group under addition abelian group, that only we will take and we will enter ring. After that, two property have to satisfy: associative law under multiplication and distributive law. If these three conditions satisfying means, that is called a ring. After the ring with unity have. With unity means if that ring under multiplication identity existing, then that is called a ring with unity. Otherwise, can tell ring without unity. Commutative ring means under multiplication commutative law will satisfy, then that is called a commutative ring. And when both will satisfy under multiplication, that time we can tell commutative ring with unity.
Sir, sir, then closure law under multiplication, it will also satisfy, right?
Where?
Ring.
Closure law. That is already have no binary operation when telling. That is no need to tell here. When
Okay,
addition and multiplication are binary operation telling, then closure law automatic solving have.
Okay, sir.
That is no need to write special. Next we will see unit element definition. This much also we no need. We are not going to satisfy this property and all. For us, no need. Unit element of ring R means which element, a non-zero element, multiplicative inverse will exist for R, that is called a unit element. In group theory, Zn group we saw under addition, modulo n, abelian group. For that one example, I choose Z6. Here, if you will try to satisfy property of ring, then already Z6 we know abelian group under addition. Only you have to choose 3 elements from Z6 and under multiplication, closure law have to satisfy, and distributive law have to satisfy. This and all no need to verify, must will satisfy. This and all not our duty. You want, you can verify, but no need. Must will satisfy this and all. So Z6 under addition modulo 6 and under multiplication modulo 6. Also, this is a commutative ring with unity also will happen. Here one is multiplicative identity we will tell. And any two element if you will choose from Z6, commutative law under multiplication must will satisfy. So Z6 we can tell is a commutative ring with unity. Unit element if you will find multiplicative inverse. First non-zero, so 1 inverse will come 1, no problem. 1 into 1 is 1. 2 inverse, 3 inverse, 4 inverse, 5 inverse we have to find. Multiplicative means a into x we want 1. Then x will be the multiplicative inverse of a. So 2 what you will multiple, then 1 will come under multiplication modulo 6. Does not exist will happen. 2 has no multiplicative inverse. 2 into 3, 6, modulo 6 will be 0. 5 inverse will exist 5 itself. 5 into 5, 25, modulo 6, 24, remainder will come 1. So 5 inverse will be 5. So unit element of Z6 is 1 and 5. I think you have remember unit group, UN group. U of 6 group elements are also 1 and 5, only relatively prime elements. I told already that UN group is unit group also telling. Name later I will tell why unit group. Because this is the collection of unit element of ring Zn. So any type of Zn always a commutative ring with unity, and unit elements will be U of n, all relatively prime elements. You can try with Z5, Z7, Z8. like that. Set of integer is an abelian group. Under addition already we saw. And under multiplication must will satisfy commutative law, any type of ABC if you will choose from Z. And commutative law also will satisfy. This and all not our exam purpose. No need to verify. Time loss, don't do. Set of integer must will be a ring, and this is commutative ring also. Here one is a multiplicative identity. And any two element if you will choose from Z, commutative law under multiplication must will satisfy. We can write set of integer is a commutative ring with unity. Unit elements can tell multiplicative inverse element, multiplicative inverse element, non-zero will happen. One must be 1 into 1 is 1, and minus 1 also. Minus 1 into minus 1 will be 1. Another no anything. 1 and minus 1 will happen. Because 1 inverse will be 1 and minus 1 inverse also will be minus 1. Only two elements will be the multiplicative inverse element of Z. No other. Next we can find non-commutative ring also we can find by the help of matrices, n cross n matrices over the field or any ring also. Z, real number, complex number, rational number, any ring. M and R. R is a ring. So M and R in this a multiplicative identity will be In, but commutative law won't satisfy. So we can write this is a non-commutative ring with unity. Unity will be In. And non-commutative why telling? Because under matrix multiplication, AB equal to BA for all A comma B belongs to M and R is not possible. So non-commutative ring with unity. Same type, same real number we can write is a commutative ring with unity. Same set of rational number is a commutative ring with unity. Set of complex number is a commutative ring with unity. Like that, right? Hereafter we will go subring. Subring meaning just a subset of R and will satisfy ring property, that is called a subring. But we are reading this subring related subgroup, subspace, every place is same type only we are seeing. If S is a subset of R, then every property no need to verify. Just closure under addition and closure under multiplication, whatever operations are there. Here A minus B belongs to S I am writing. This is two concepts satisfying, closure under addition as well as additive inverse existing. So these two property you can tell closure under under subtraction and closure under multiplication. If this satisfying means that is a subring. But this also no use for us. We are not going to do like this. We have concepts by the direct also we can do. But why I am giving? Because this is very common concept. Maybe in exam hall they can ask either subspace or subgroup or subring. Every place is just closure under their operation will show means that is a vector space, vector, subgroup, subring, everything. Already we know about subgroup. Now we have to know subring. Very easy. Already we know Z6 is a ring. So as a group, all subgroups we know. 1 order, 2 order, 3 order itself. Every subgroups you write. And every subgroups are subring only. Nothing new subring won't come from any place. Whatever subgroup we saw, this all will satisfy subring property. All will be the ring. And here also same, proper trivial subring, proper non-trivial, this also proper non-trivial, this is improper trivial. So direct you can find as a group whatever D order subgroup we saw in Zn, D divides N, that all are subring of Zn. Finish. D order subring. Ring and field, no any big problem or tension. Whatever group we saw under addition, all concepts we can write as a ring. Subrings and all we can tell which place if multiplicative identity if one not have, we can tell subrings are without unity. We can see, we have to find, we have to check maybe any unity, multiplicative unity is there or not. Always depend on subring. One will be the multiplicative identity. So you have to verify for depend on subring who is the multiplicative identity. If is there, we can tell that is with unity, otherwise without unity. Depend on multiplication modulo n. Set of integer we saw is a ring, and subgroups we know for this. All subgroups one order identity. Another nz, for all n belongs to natural number, respectively n is not equal to 1. And next S3 will be Z itself. So infinite subgroups have 2Z, 3Z, 4Z, this all. So infinite subgroups have, these all are only subrings. This NZ we can tell subring without unity, because here 1 won't be there, 2Z, 3Z, 4Z, nothing multiplicative in identity 1. This is the subring without unity. Same, this is proper trivial subring, this is improper trivial subring. All NZ are proper non-trivial subrings. All subgroups are subring, direct, right? No need to worry. Just now I wrote MNZ. MNZ, MNR, MNQ, all are commutative ring, non-commutative ring with unity. If MN ring place, I will use 2Z. 2Z, 3Z, 4Z means, suppose I will choose KZ. What is K? For all K belongs to natural number, but K is not equal to 1. Means 2Z, 3Z, 4Z, if like that I will choose, then must this is a non-commutative ring without unity. No identity element here. IN does not belongs to MNKZ for all K. Whatever we'll choose, MN2Z, MN3Z, MN4Z, MN5Z, everything. We can write set of integer is a subring of real number, rational number, complex number. Real number is a subring of complex number. Rational number is a subring of real number, also complex number. Right. Very easy, everything. Here also can tell every ring has at least two subring. Identity means 0 and itself. Every ring we can tell set of real number is a subring of itself. Everything complex, rational, everything subring of itself. Zero is always without unity subring. Identity 0 is always without ring, means subring without unity can tell. Set of real, complex, rational. We saw this is a ring, but unit element not saying, no. What is the unit element of real number? Unit elements of R. Non-zero multiplicative inverse element. Tell. These are all are real number. Anything you choose, non-zero must multiplicative inverse will exist. All non-zero number can tell. Ring type don't write, element writing, no. R star. All non-zero elements. Complex, direct, complex is right. Non-zero complex C star can write, no problem. Zero only non-zero complex, no problem. Q. All non-zero numbers are multiplicative inverse will exist. Either real, complex, rational, anything. Z box I is a Gaussian ring of integers. Z box I cardinality will be infinite. Countably infinite also can tell. And this is commutative ring with unity. Unity will be 1 plus 0 I. Commutative also will satisfy. Multiplicative inverse element, if you will find unit elements of Z box I, means you have to find A plus IB belongs to Z box I, then A plus IB inverse have to find. So multiplicative inverse of A plus IB is equal to A by A square plus B square minus I into B by A square plus B square. But here you have to choose A and B from integer, and this complete belongs to, we want Z box I. So which type of A and B are suitable? Because A by A square plus B square, this is not an integer, this will be the rational P by Q form. So here multiplicative inverse element will be 1, minus 1, I and minus I. Only 4 elements will be. Means A equal to 1, B equal to 0, A equal to minus 1, B equal to 0, A equal to 0, B equal to minus 1, and A equal to 0, B equal to 1. This only 4 if you will check, then only multiplicative inverse will contain Z box I. Otherwise another anything if you will choose does not belongs to Z box I. Also we can tell Z box I is a subring of C, means complex, subring of ring complex. Zn box I is a Gaussian ring of integers modulo n have to tell, and this is cardinality finite will happen n square because n arrangement from Zn, and this is also commutative ring with unity, but here unit element we have to find depend on modulo n. Generalization can't give. So whatever Zn box I, if you will choose for that n, you have to find same like that multiplicative inverse, and you have to choose AB from Zn and have to check that Zn element again coming or not. So here generalization you can't, we can't give. Depend on n, we have to find. Zero divisors definition is if two non-zero element, if you will choose from commutative ring and their product will be zero, then both are called zero divisor elements we can tell. And this is, I'm not writing distinct, itself also possibility. If A into A, I'm not, just I wrote two non-zero, I'm not writing distinct. Sometime A into A itself zero will come. So at least one will be the zero divisor possibility in that case. Integral domain, when R commutative ring with unity, after that no zero divisor element, then that is called a integral. You see Z6. This is a commutative ring only, and here 2 and 3 multiplication if you will choose, modulo 6 0 will come. 3, 4 if you will choose, 12 0 will come. Another no anything. Meaning we can tell 2, 3, 4 are zero divisors element of Z6. So we can finish if zero divisor element means that is not integral domain also. So we can tell this is not integral domain. You can see for Z4. Here 2 into 2, modulo 4, 0. 3 into 2, 3 into 3, no. Here 2 is only zero divisor elements. Anyhow, Z4 we will tell is not integral domain. You can choose for prime Z5, Z3, that and all integral domain will come, no zero divisors. Suppose Z5 will choose 0, 1, 2, 3, 4. You can see any two non-zero element if you will choose, their product must non-zero will happen here. You can write also any two non-zero element if we will choose from Z5, their product must be non-zero. So this is integral domain you can write. Zn, if n is not a prime, then always never will be an integral domain. But prime case always integral domain. Set of integer is a commutative ring with unity. This is an integral domain, can write. No zero divisors. Any two non-zero element, if you will choose from Z, must their product will be non-zero. Set of real number is an integral domain. Complex is an integral domain. After that, rational number is integral domain. Z box I, we saw a Gaussian ring of integers. This also must be a integral domain. Any two non-zero, A plus IP, if you will choose A plus IP and C plus ID, you write otherwise non-zero. Then their product will be a non-zero will happen. Zn box I you have to verify. Because of modulo n, their integral domain, not integral domain possibility. Zero divisor will come. You will check. Suppose Z2 box I am choosing. A plus IP, A and B from Z2. So Z2 box I element will be 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. So Z2 box I has 4 elements. In the two non-zero elements, their product will be 0. Then we can tell this is not integral domain. Itself also possibility. Two non-zero means itself also. Suppose 1 plus I into 1 plus I will do, means 1 plus I whole square. So 1 plus 2I, I square minus 1. See, modulo 2, 0 will go. So 1 plus I is a divisor element. In Z2 box I. So Z2 box I is not integral domain. You will check Z3 box I, check it. And Z4 or Z5 box I, check it. You do now, otherwise homework do. These three you have to check zero divisor elements or not. You have to check this is an integral domain or not. If no zero divisor element, you can write not integral domain. Must check, very important this. We have to use more places. Just element right, cardinality is finite only. Element right and find zero divisor elements. Z3 box I, if you will solve, AB from Z3 will happen and elements total 9 will come. So Z3 box I, total 9 elements are this. If you will take any two non-zero elements, their product non-zero if coming, means this is integral domain. Means you have your work, this is, I can't do anything. I will write direct. Modulo 3 have to use. And this is integral domain only. Two non-zero element, if you will choose from Z3 box I, their product must be non-zero will happen. Z3 box I is an integral domain of order 9. Finite. You can verify. You have to verify must. Don't neglect, otherwise problem will come. Z5 box I is not integral domain. I am writing here direct. You have to verify counter. Here total 25 elements will come. So this is your work. Who is the contradiction giving? This is not integral domain. Find contradiction. Means two non-zero elements choosing, their product must be zero. Z4 box I is very easy. Z4 box I is very easy. Why easy? I'm telling. Because Z4 will contain in Z4 box I, correct? Means Z4 every elements will be here when B equal to 0. 0, 1, 0, 0, 0, 1, 0, 2, 0, 3, 0. So Z4 must will contain in Z4 box I. And already I told Z4 means Zn except prime is not integral domain. Direct you will get contradiction for Zn. Z4 is not integral domain. Why? Because 2 into 2 is 4, modulo 4 is 0. 2 is 0 divisor. And 2 is belongs to Z4 box I also. So Z4 box I has 0 divisor element. So this is not integral domain. And every places you will see, if suppose Z6 box I, if you are checking. Here also you can write Z6 containing in Z6 box I. And Z6 is not integral domain. Because 2, 3, 4 are 0 divisor element. Already just now I told of Z6. So this elements belongs to here also. So these are 0 divisors of Z6 box I. So Z6 box I is not integral domain. But prime case you can't do like that. You can see Z5 box I, Z5 will contain here. But Z5 is an integral domain. So this is integral domain, you can't tell like that. We have contradiction is non-prime case. Non-prime case contradiction have. So we are telling like that. But if Z5 is containing in Z5 oxide and Z5 is integral domain, so Z5 oxide is integral domain, not like that. You have to verify. Maybe other contradiction we are getting from Z5 oxide, any other element. So we can't go short trick anything, short concept in prime case. Non-prime case direct we. So you have to verify. You verify and check this is homework. This also Z3 oxide also. Everybody tomorrow can give time. Tomorrow evening 5 to 7 or 7:30 evening time. Only tomorrow. After the next Saturday, Sunday again class. If okay means I will put. So tell me properly. 5 to 7, 7:30 like that. Mostly everybody silent have, so I think no any problem. So tomorrow I will take class. 5 to 7 or 7:30, 8 o'clock also maybe, but hardly 7:30. You are silent means everything okay. Some message came. Message giving. Okay. Okay, then everybody okay, only telling. Okay, tomorrow evening. Tomorrow evening we will take class 2 hours. Q box root D type field we will see in next class and all. Which type of elements have we have to use more places about this. So before I am writing, Q box root D elements are A plus B root D form, and this is a field. Field is still not giving. So just you think this is a commutative ring with unity, can write like that. Field time again I will write. Also two non-zero element if you will choose, then this is an integral domain only. Z box root D. Z box root D also will be integral domain. For all D. Set ring matrices form, you can tell not integral domain, because product of two non-zero matrices we can prepare null matrix. Any ring, real number, rational number, complex number, add any ring. Any type of ring, if you will choose, this is not integral domain will come. Two non-zero matrices, if you will choose n cross n, their product null matrix will come. Easy only. 2 cross 2, suppose if you will go 0, 1, 0, 0, choose. Another one, 0. With this side choose. What problem? No, this side, direct one come. This side can choose. This product what will happen? 0, 0. This one, again mistake. Same choose, otherwise what problem? A equal to B. Same also. Same is that place, no? Then this check it. This is okay. This won't come. This product will be 0. So product of two non-zero matrix will be non-zero. Sorry, will be 0. We can get contradiction any order, 2 cross 2, 3 cross 3 in any ring. Z, rational. This is common for everything. This is set of integer tail, real tail, complex tail, rational tail. So not integral domain. external direct product of groups we saw component wise operation. Here already this is a ring, so component wise two operation will happen, addition and multiplication. Component wise addition will happen and component wise multiplication will happen. This is also we can tell external direct product of rings. Tomorrow we will see example for this. We saw external direct product, same only that only this here will be a ring. Whatever we saw under addition, here operation will happen and multiplication. Tomorrow we will see hereafter. Tomorrow evening 5 o'clock. Sharply 5 o'clock I will start class. Huh? Don't think. So 5 o'clock to 7, 7:30, 8 o'clock also possible. Okay, then tomorrow we will meet evening time.